So shall we start by defining what a Markov chain is?
Sure.
Okay.
I guess the easiest way to start defining it is just to talk about a couple of different things we're going to need to, I guess, set up first.
Okay.
So the first thing I want to talk about is imagining just a sequence of variables.
Okay.
We're going to call them xt. X denotes the fact it's capital, so it's a random variable.
Okay.
And t denotes that there's some sort of sequence or time to it.
Okay.
So if we want to write down a series that's like this, so those are supposed to be squiggle brackets.
That's all right.
And we can write t equals 1, 2, ... to whatever number we want to go to.
Mm-hmm.
So we'll call this sequence just x.
Okay.
Now, there's a bunch of different sequences you could make, and a Markov chain is a very particular kind of sequence.
Okay.
It's a sequence which satisfies essentially two basic conditions. I guess three if you want to get into the fact that one of them is kind of two independent ones rolled into one.
Okay.
The first of these conditions is that x at t is within some finite set, or at least countable set. So s could actually be infinite as long as it's countable.
Okay. Can you give a quick example of what you mean by that?
Well, an easy example for a finite set would just be, it could be either the number 1, 2, or the number 3.
Okay.
An example of an uncountably infinite set would just be any number from 1 to infinity.
Right.
All integers.
Okay. All right.
So that's the main idea of what a Markov chain is, but the core, I guess, mechanic that holds the whole thing together, and this is a mechanic and assumption that essentially not only dictates Markov chains, but also a whole number of other stochastic processes, is called the Markovian assumption.
Okay.
So if we have this sequence and x is a random variable, we can talk about the probability that the random variable has some value.
That's all right. That's all right.
Don't get hung up on the fact this is a little x. It's a general dummy variable.
Okay.
So this is just saying the probability that this value is equal to one of the values from s.
Right. Okay.
We can ask about this probability.
Okay.
More specifically, we can talk about the fact that because this has a time component to it, we can talk about the conditional probability.
Okay.
Of x at t, given x at t minus 1, all the way back to x at 0, which is to say the very first value in the chain.
Okay.
We can talk about this conditional probability.
Right. So this is, you're writing a conditional probability of the random variable at the current time index conditioned on the values of the random variables in all of the previous time indices.
Exactly. So we're essentially saying we want to look at the distribution of the random variable at this time, given that we've watched this process up until this point.
Right.
And we know exactly what its history is.
Right. Okay.
Now, the really convenient thing about the Markov assumption is that it makes this much easier to deal with by essentially killing everything beyond the very last step.
Aha. Okay.
So what ends up happening is this whole large probability ends up just equaling, I guess I'll write it out, in a spot where I have a bit more space.
Later on we can erase the stuff on the top. Don't worry about that.
More or less, the Markov assumption just says that the current state depends only on the last state. I wish I were quicker at writing on a whiteboard.
No worries, no worries. Okay, so hopefully everybody.
I don't know how you can read that, but
hopefully everybody can read that. So what Chris has written here is that p of xt equaling small xt is conditioned on only x of t minus 1 being equal to little x of t minus 1. Okay?
Actually, I'm going to try writing it a different way, and hopefully this will be easier to see. And the second part of this, and this is the part where I say this is kind of
try to press against the board a little harder.
Two different assumptions, as it were. So this first part says, I only care about this last state.
Right.
And this second equality says that, and this condition only depends, or this condition is independent of time, which means to say that this probability is not going to change if t is 10 steps in the future, 20 steps in the future. If we know the past state, these probabilities will remain the same.
Right. Right. Okay.
That's essentially what this last step is. So that's two things kind of rolled into one.
Okay.
But if we have this, which is called time homogeneity, it's homogeneous in time, then, and we have this lack of conditioning on anything past the last state, and we have a finite sample space, that's all you need for a Markov chain.
Okay. All right. So let's just recap. So I think you said three things there. The random variable, the sequence of random variables has to belong to some set, and it could be an infinite set.
Countable or finite set.
Okay. So could it be an infinite set, or
it could be a countably infinite set?
It could be a countably infinite set. So as long as it's a countable,
you can consider a Markov chain. Yeah.
Okay. And the second condition is that the probability of the random variable in the current state is dependent on only the value of the random variable in the previous state.
Yes.
And then the third is the time homogeneity, which says that the probability of any one random variable, you know what, actually, I don't know how to articulate that third condition. So please
I can articulate that last condition a little bit more clearly. Essentially what it says is, let's consider two states. Right? Okay. I'm going to remove this subscript to make it easier. We'll consider two states, x and y.
Sorry, Chris. Here. Let's just do. Let's step back.
So, that's pretty light.
Yeah, it's pretty light, and you know what? We could use a lot more room here. So. No, this is why this will make this a lot easier for you to write here. Okay.
Yeah, I gotta be conscious of the fact that computer camera is not as sensitive as our eyes.
No worries. Okay, so if you could please just press a little harder on the board and use the thick.
Yeah, that's what I'm trying to do.
There you go.
That's a bit better. Yeah. So we just consider two states, x and y. Then the condition essentially says that the probability that x at t equals x given x at t minus 1 equals y is exactly equal to the probability that x at 1 equals x given x at 0 equals y. Which is to say, the probability of going from y to x does not depend on the value of t. Which means that no matter how long you run the chain, this probability is a constant. Because you could think of some process where the probability of going from one state to another really does depend on the time you're at, how many steps you've gone through the process.
Oh, okay. So
you could have something where the probability of making this transition decreases or increases in time. But this says that it's a constant. It doesn't matter what time step you're at, this probability will remain the same, which is very important for a lot of the analysis we do.
So are you saying that, let's say if for this probability right here, this is equal to 0.3.
Yeah.
Are you saying that now we're specifically talking about t is equal to 1 and t minus 1 equal to 0. Let's say if this is equal to 0.3.
Yeah.
Are you saying that for t at p of x at 57 equals x, p of at 56 equals y, that's also equal to 0.3?
Yeah, exactly.
Oh, okay.
Doesn't matter how far into the process you are, that probability stays constant.
Oh, okay. Right. Okay. So I think yes. I think I understand the difference between those last two conditions now. So the second condition says that the probability of the random variable having a particular value is dependent on the previous state, but that conditional probability could change from one time from one time to the next. So the third condition is making even more narrow and saying that probability stays the same no matter what time point we're talking about.
Exactly.
Along this index. Okay.
Essentially, it's saying that the dynamics of the system aren't going to change dramatically in time.
Right.
We have some set mechanics, some set dynamics, set probabilities, and those will be constant as long as we run the chain.
Right. Okay. Okay, thank you. I appreciate that clarification.
Well, it's important because, like I said, those two are typically wrapped into one, which is the time homogeneous Markov assumption, but they really are two independent, I guess, assertions, if you will.
Yes, yes. Okay. Good. I'm glad that we clarified that.
But the Markov assumption is actually really important because it allows us to forget, I suppose, a lot of the information about this system that we would otherwise need to worry about.
Okay.
So if you imagine conditioning on a process that's been running for 50 or 60 steps, then you're doing conditioning on 50 or 60 random variables.
Right.
And it's going to be very difficult to get anything accurate out of that.
Right.
This idea of being able to forget most of the past and remember only the last state is a really useful assumption for analysis.
Right. Okay.
And if you think about it, some people might say, well, this is a very strange assumption to make. Surely history matters much further back. The way I think one of my professors always put it was he said that imagine you're applying for a job. They're not going to ask you for your elementary school grades or your junior high grades, or many of them won't even ask for your high school grades because you've done university now or you've done some training program now. And so they only really care about the most recent education you've had. They don't care too much about your history beyond that.
Right.